In our research, we are trying to search for and characterize the unknown. We are trying to produce new kinds of particles and interactions and study these interactions to put together a clearer picture of how the universe works at its most fundamental level. To find answers to understand physics beyond the standard model, what we're trying to do with the detector is take a snapshot of the aftermath of collisions of protons, and from that snapshot to look backwards and try to figure out what the fundamental interaction underlying that event was.
To achieve this, ARCE runs computer simulations that replicate as closely as possible these particle collisions.
We can't understand the nature of interactions by only looking at one event. That's impossible, because the laws of physics don't tell us what happened in a specific event. The laws of physics tell us the relative probabilities of different things taking place in a proton-proton collision. So, in order to quantify what we think might have happened, what we often do is simulate particle collisions and their interaction with the detector, and compare a lot of simulated events to a lot of recorded events. And if this comparison matches up, then we think we understand not only what our detector was doing, but also what took place in that initial collision.
ARCE's simulations use the Monte Carlo technique. This method, named for the city famous for its casino games, is analogous to rolling dice over and over again to figure out the probability of every possible combination. But in this case, instead of rolling dice, they are simulating particle collisions.
The Monte Carlo uses random number generators in the computer to decide what particles will be produced and what angles they will move towards and what energies they will have and how their subsequent interactions will take place. Because these processes are inherently random. And since they're random, we can only learn for them by studying a large number of similar interactions. And the Monte Carlo allows us to generate large numbers of simulated interactions, which we can study to our heart's content before we look at the real data. Now, if you see a rare event, something that you don't understand, what you'll do is go back to your Monte Carlo, where you've plugged in all of the physics that you already know. You've plugged in the standard model. And you'll take that Monte Carlo and analyze it with an identical set of software tools to reconstruct events. And then you'll compare the Monte Carlo to the events that you've seen. If that weird event is still there, and it's never generated by your Monte Carlo, but you've seen it many times in data, then it's a signal that there's something new that you don't understand.